In this video, we discuss about modeling with differential equations. The focus is still on modeling change, as it has been in our last videos, but this time we focus on processes that take place continuously in time. We start in this video the discussion about a very different kind of modeling than what we've seen so far in this course, modeling with differential equations. Continuous mathematics is without a doubt the most developed part of mathematics, with great many tools and techniques available. It's not surprising that modeling with differential equations is the most popular technique in life sciences, and not only. In this course we only consider ordinary differential equations, in short ODEs. Other types of differential equations exist, but they are beyond the scope of this course. The modeling strategy when formulating an ODE-based model is to think about the change in all our variables, who influences the change in their current value, and in what way. Here is an example. Let's say that we have information about the change in the size of a population and that it can be written as delta p, the change, is the difference between the level of the population at time t plus delta t minus the level of population at time t. And let's say that we know it's proportional to what we have at time t, so it's going to be k times p of t times delta t. This is a difference equation. Time is treated discretely. We only have a discrete set of time points. So this can be reformulated as delta p over delta t is equal to k times p of t. The interpretation of this formula is that the average change of p over the interval from t to t plus delta t is k times p of t. Now here is the crucial ingredient. If we make the length of the interval smaller and smaller and allow it to converge to t, what we get on the left hand side is the differential of p at time t, which signifies the instantaneous rate of change of p at time t. In other words, by moving from a difference to a differential, we have moved from reasoning about the average change of p over some time interval to its instantaneous rate of change. Development of calculus was triggered by the study of motion already in the 16th and 17th centuries. They were studying some particles traveling from some point S1 at time t1 to some point S2 at time t2. And delta S over delta t is the average velocity during this time period. So we could have a plot like this, where here we would have the time, and here, here we would have S, and here we would have t. And this particle travels from S1 at time t1 to point S2 at time t2. And this would be delta S here, and this would be delta t here. So as we make this time interval smaller, then the difference between, or the ratio delta S over delta t is going to tend to the value of the differential at time t1 as delta t goes to 0. Remember that the studies that led to the development of differential equations were motivated by the drive to understand planet motion. In particular, when constructing lenses for the telescopes, there was a need to know the tangent to the curve describing the lens surface. If we look at the shape of a lens, we can see that the difference delta S over delta t that we looked at before can also be interpreted as the slope of this blue line in this figure that goes through the 2 points A and B. The line is called a secant. As B approaches A, the secant changes, and eventually by the time B gets very close to A, the secant becomes the red line in this figure, which is the line touching the curve in only one point, in other words, the tangent at point A. And that's exactly the intuition behind differential equations if we think about them with this geometrical interpretation. We want to calculate the tangent at point A, and that is the difference in s divided to the difference in t, calculated over a smaller and smaller time interval. To make these matters concrete, here is a famous example, the Malthusian model for population growth, developed already in the 18th century. We know in this model the population size p0 at time t0, and we would like to predict the population level at some later time t1. And the model considers only two factors. One is the birth rate, and the other one the death rate. Obviously, this is a very elementary oversimplified model for population growth that ignores many other important factors such as immigration and emigration, living space restrictions. It ignores the fact that the birth rate is in fact not constant and it's influenced by many factors. The death rate is also influenced by sanitation and public health and wars and pollution, and so it varies quite a lot over time. And this leads to this oversimplifying assumption that birth rate and death rate are constant. However, to construct a model based on these assumptions, we can write the equation for the change in the population as follows. dp to dt, in other words, the change in population level, is influenced obviously positively by the birth rate, so it's b times p of t, and negatively by the death rate, so it's minus c times p of t. So in other words, this is exactly b minus c times p of t. We can even calculate the solution of this equation. I don't go into how this solution is calculated, and in fact in most realistic cases we will not be able to find a solution to this type of model. But this model is so simple that it does have a solution, and it looks like this. P of t equals p0 times e to power b minus c times t minus t0. We can even plot this model to see how it looks like. We can first check what the values of p0 and b minus c could be in this model. To do this, we can check the population level, say in the US, at two different time points and plug these values in the model. When we do this for the population levels in 1990 and in 1970, we will find out that b minus c should be set to 0.01. To verify the model, we can now calculate what the model predicts for the population level in different years and compare it to the census values. So we can predict the population in 2000, and the model is going to give a value of about 303 millions. And in fact, the real population level in 2000 was something like 281 millions. And so the model prediction is about 8% off the mark, which is not too bad. We can take now a look into a prediction for the future and check the population level predicted by this model for year 2300. We obviously don't have the real value for year 2300, but really it is impossible that it could ever be this huge number. And so it's clear that the model becomes unreasonable over long periods of time. In fact, it's not difficult to see why this model fails over long periods of time. The population in the US has grown steadily over the time period that we had data on for this model, and so the model is trained to predict continuous growth. Remember that its birth rate and death rate are assumed to be forever constant. And so, over a long period of time, the growth predicted by the model leads to such high numbers, while ignoring that of course this kind of absurd growth is unsustainable. We can try to write another model for the population growth that's more reasonable over a longer time interval. Our initial model, dp to dt equals k times p of t, where k was a constant, the birth rate minus the death rate. So what if we this time assume that the growth rate is in fact not a constant, but it depends on the population level, and that in fact the growth rate is going to slow down as the population grows, and get closer to zero as the population approaches a maximum sustainable level. An easy way how to come up with such a growth rate function is to choose simply something like this: k equals some constant times m minus p of t, which captures well our wish that k decreases as p increases and that it gets zero when the population reaches a maximum level m. So our model becomes dp to dt equals r times m minus p of t times p of t. As a matter of fact, this version of the model is also historical, having been proposed in 1920 with a predicted maximum level for the US population around 200 million. The figure was determined by looking at the population level starting from 1790. The evolution of the model looks like this. Such a population model for US was proposed in 1920, with M being about 197 millions, determined based on census figures for 1790, 1850, 1910. So when verifying the model gives very good predictions up to 1950, but too small predictions for 1970, 1980, 1990, and 2000. And that's of course not surprising, because immigration and wars and advances in medicine are not considered by this model. But here is a surprising thing. In fact, verifying the model on the growth of East in culture gives excellent predictions. We continue this discussion in the next video.